Hi, my name is Cameron Stewart, and I'm excited to talk to you today about cross-entropy loss for multi-class classification in neural networks. Let's talk about some background on cross-entropy. Like, what even is it? So in the text, you'll see it says it is a measure of the difference between two probability distributions for a given random variable or set of events. What does this mean in the context of neural networks? Well, in a neural network, you know the predicted probability of each individual class, and you also know the actual class in the training data. Using this data, you can understand the level of surprise of that actual class compared to your prediction. This is essentially what cross-entropy loss is telling you. What is cross-entropy loss used for? It is used to optimize binary and multi-class classification models. And these models are typically traditional machine learning models, such as naive Bayes, LDA, or deep learning applications like neural networks, which is what we're discussing today. The cross-entropy loss formula shown here is just the negative of the summation of the binary indicator of which class is the actual class, multiplied by the log of the probability of each individual class. And if you look a bit deeper, you'll notice that that binary indicator is only 0 or 1. So any class that is not the actual class will have a 0 in that y value, and therefore that term will go away. So the only class that really matters in this application is the actual class. So looking at the right, when you look at the cross-entropy of the actual class, the predicted probability is on the x-axis and the cross-entropy loss is on the y-axis. The higher the predicted probability, the lower the cross-entropy. And that's because with a high predicted probability of the actual class, there's not very much surprise that it was true. And with a low predicted probability of the actual class, you'd be very surprised. Therefore, there'd be high cross-entropy. And you are trying to minimize cross-entropy. So let's take a step back and say, what is a neural network? So here's an example of a classification neural network where you have an input layer with 4 variables, and it steps through 2 hidden layers. And in a real neural network, you can have as many hidden layers or nodes or neurons, as they're also called, in those hidden layers in your network as the application calls for. After going through these hidden layers, you'll arrive at the output layer, the last layer of the model. And these will represent each of the individual classes in a classification problem. So here we have classes A, B, and C. And each of those nodes or neurons after the input layer, you can see here how the information flows through it. So you have your input values from the previous layer. It's multiplied times a weight. Each of those values is then summed together. And then a single bias term is added to that previous value. And that is inputted into an activation function. The activation function is a choice by the user of the model. And then the output is then the output of that node or neuron. And then it is moved to the next layer, or if it's going to the output, or if it's for the output layer, then that is just the output of the model, or for that class. So let's apply cross-entropy loss in a neural network. The example I chose is the iris dataset because I know most data scientists at this point are comfortable with the iris data. And we'll see here, the inputs are as expected. It's the sepal and petal length and width. It moves through 1 hidden layer with 3 nodes, and the output layer has setosa, versicolor, and virginica. And we are trying to predict, based on those inputs, one of those 3 classes to be correct. So based on some inputs, and in this example, the inputs don't really matter. We're focused on how to transform the outputs into cross-entropy. So let's focus on the outputs for a single observation for cross-entropy. And you can see here, these are how the labels and the nodes on the left, what they represent. And so here, looking at the raw output, what you should notice is that these values are not between 0 and 1 as you'd expect probabilities to be, and they also don't sum to 1. And that's because these values are just raw values, they are not probabilities. But what we do know is that the max value represents the class that is most likely to be the actual class according to the model. And that's also true for the second most likely value is is predicted to be the second most likely value, and so on, based on the model. So what you might think is, well, if we know that, then we know that we should just look for the max value. We know that's the predicted class, apply a 1, and then look at all the values beneath it, just apply a 0 because we know they're not the predicted class. That's what argmax does. That is exactly how it works. It just searches for the max value of your raw outputs. Argmax is great for test data, but it cannot train your model. Cross-entropy needs predicted probabilities, and that level of granularity is not in argmax. So what you need is softmax. So what is softmax? Softmax is just a normalized representation of your raw outputs so that they become predicted probabilities. As you can see here in the equation, it's just the exponential of the raw output divided by the sum of the exponential of all the raw outputs. Let's see it in action. Here, you can see the denominator is the same for every node, for every class. It is the exponential of all the classes added together, but the numerator is what's changing. It is just taking the exponential of that raw output for that specific class. And here are the outcomes. And what you'll notice is now these sum to 1, and they're also between 0 and 1, just as probabilities should be. One thing to note is that these probabilities should be taken with a grain of salt, as there will be some level of variability based on the random initialization of the neural network. But typically, you'll still get the same output of the most likely predicted class. So as we move to cross-entropy loss, this is a reminder of what the cross-entropy loss function was that we reviewed before. And we'll assume that the correct classification for this example observation is setosa. So now let's calculate cross-entropy. And as I mentioned before, the binary indicator for the other classes that are not the actual class are 0. And so these terms will go away. And the only class that factors into cross-entropy is the actual class, and is the negative of the log of 0.57, which equals 0.56. Looking at our loss curve, we can see this is exactly what we expect as the predicted probability and the cross-entropy align where that x is with our result. So looking at, we did all of these equations, and now we did this for only one observation. But if you're training a model, you want to train many observations. So let's go ahead and add some additional observations with different cross-entropies and also different actual classes. Now, how do we aggregate these cross-entropies? Well, you just take the sum. And here the sum is 1.31. And typically it is represented as the mean cross-entropy, and that's just taking the average of those. That is just in case the aggregation is of different amounts of training data. Backpropagation is out of the scope for this presentation, but just an important note I wanted to touch on is that typically in regression for neural networks, the derivative for the backpropagation never changes for the weights and the biases. For each individual parameter, it is consistent. But in classification with cross-entropy, it actually changes based on what the actual class is for each observation. So you have to be careful as you step through each observation in the training data. And you'll see this as you begin to study this a bit more. So in conclusion, we answer questions on what is cross-entropy, why do we use cross-entropy, how do argmax and softmax relate to cross-entropy, and how to calculate cross-entropy. And what I really advise for future study is to really dive into how the backpropagation works for cross-entropy, and it'll really help connect these concepts. And I just want to show you some of these great references. I really recommend looking into these. And this is what I used to create this presentation. And that's everything I have. I would like to thank you for listening, and I really hope you learned something.